Good morning. Now, anyway, others may join later. But we'll start this today's session. Now, in today's session, we will talk about the minimum cost spanning trees. Now, this is also a topic which comes under greedy method, or greedy approach, or greedy strategy. Now, we have seen 0-1 knapsack. We have seen job sequencing with deadlines. And this is the other topic which comes under the greedy method, or we solve the minimum cost spanning tree problem with using greedy method or greedy approach. Now, graphs, usually we create a minimum spanning tree from a graph actually. So graph is nothing but they have several applications. For example, graph can represent airports, and the edges may represent the flight paths, and each cost may have a weight, and the weight may represent the flying time, or the weight may represent the cost of the ticket, or several other cost metrics can be applied here. Now the question is, what is the shortest path from one place to the other? Though this question generally is the comes into mind of everyone. The shortest path problems and all are solved. There is a different technique to solve all those things. But what we try to do here in this minimum cost spanning tree is that we take a graph and create a tree from that graph. And that tree, all the edges combined together, should have the minimum cost. So let us consider we have a graph G where V represent vertices and E represents the set of edges. Now, graph, you can have any edge. A graph may have any number of edges, doesn't matter, but this is a sample graph here. Take it. Now, for this graph, a spanning tree is defined as T, a set of vertices V, and edges E dash. Now, when we say set of vertices V, that means all the vertices of a graph should be there in the tree. And this T is a spanning tree if and only if T is a tree. When we say T is a tree, that means there should not be any cycle. There should not be any cycles. In this case, if you see this graph, we have vertices 1, 2, 3, and 4. Now, if you look at the edges, there is a cycle from 1 to 3, 3 to 2, 2 to 1. But tree cannot have a cycle. So that is the point we need to remember. And here in graph we have E, but in the spanning tree, we say we have E dash. Now this E dash is nothing but different from E. E dash is actually a subset of E. So let us consider this, the figure which is there on the left side. Now this is a spanning tree because there is no cycles, first of all, and all the vertices are there are same as what we have in the graph, and we have certain edges. So vertices are same, and then the edges E dash is 1 to 2, 1 to 3, and 2 to 4. This E dash is a subset of E. Now we cannot have a new edge in the spanning tree. Whatever edge is there in the graph, that same edge will be used, but it will be a subset. So remember one more thing, there is no new edge we can have. We can only use edges which are there already, which are already there in the graph. Now, this informal definition leads to some of the properties of the spanning tree. The first property is all the vertices, as I said, all the vertices of graph G are in spanning tree T. So V, set of vertices V in graph and set of vertices V in the spanning tree will be same. Then spanning tree T should be connected. Remember, we may have all the vertices of graph in a spanning tree, but all those vertices should be connected. Should be connected. That is another important step there. Otherwise, it will not be a tree. Then the third property is that the spanning tree is acyclic. That is, there should not be any cycles in the spanning tree. Now remember, right, we are just talking about spanning trees right now. We will discuss about minimum cost spanning trees later. So spanning trees has three properties. That is, all the vertices in the graph will be there in spanning tree. Spanning tree should be connected, and spanning tree should be acyclic. There should not be any cycles. Now, spanning tree is sometimes also known as minimal subgraph. Minimal subgraph. So actually, spanning tree is nothing but a subgraph of a graph G. Now, why we say minimal subgraph? Because we can use minimum number of edges to create a spanning tree of a graph G. Then it's not that we can only have one spanning tree. There can be any number of spanning trees. For example, let us look at another set of edges which we use to create a spanning tree. Number of vertices will be same, but let us say we have an edge between 1 to 3, 3 to 2, and 3 to 4. These edges are already there in the graph. So this also becomes one of the spanning tree. Then again, we may have an edge between 1 to 2, 2 to 4, and 3 to 4. These set of edges are also there in the graph. So they can. So we can have several spanning trees. In this case, we have only generated 3 spanning trees, but they can be several spanning trees. Now, usually what happens is, if there are n number of nodes or vertices, then in the spanning tree, I'm talking about spanning tree. For in the spanning tree, if there are n number of vertices, then there will be minimum n minus 1 edges. There will be minimum n minus 1 edges, and this property is very useful. We say why we say n minus 1 edges, because if all the vertices has to be connected, if the spanning tree has to be connected, then we need, for n vertices, we need n minus 1 edges. We need n minus 1 edges. So this is one of the properties. So in this case, all the graphs has, all the spanning trees has 4 vertices. So we have edges as 3 as the edges there. Now, the edges of the graph are usually associated or has some weights. Now, these weights may be like example we have talked about for an airports. The flight paths may are the edges, and they may be the weights of those edges. The cost of the edges might be airfare or flying time or distance. So basically, edges will have some weight. So here what we are talking about is we have talking about a graph, a weighted graph and weighted undirected graph. There is no orientation for edges. It's an undirected graph, weighted undirected graph, which is connected. So we are talking about weighted connected undirected graph. So once we have the weights on the edges or cost on the edges, the cost of the spanning tree, each spanning tree, cost of the spanning tree will be sum of the cost of the edges. Sum of cost of the edges, and edge should belong to the spanning tree. Now, not the cost of the edges of the graph. For the spanning tree, the cost of the spanning tree is the sum of cost of all the edges which belongs to the spanning tree. So that's why C comma W, if this is an edge, sorry, it should not be C, it's actually V comma W over here. So V comma W, the cost of V comma W, summation of cost of V comma W is the cost of the spanning tree, where V comma W is nothing but belongs to E dash, not E, E dash. E dash is nothing but set of edges. So in this case, we have 3 plus 2 plus 4, which is 9. The second spanning tree has got 3 plus 6 plus 1, which is 10. And the fourth spanning tree has got 2 plus 1 plus 4, which is 7. So cost of the spanning tree is the sum of cost of their edges. Now our problem is to find the minimum cost spanning tree. Now these are three different spanning trees for this graph, but they may be several other spanning trees. So just by looking at these trees, we cannot say that this is cost is 7, so this is the minimum cost spanning tree. We cannot say, because there may be other spanning trees also which may have less than this cost. So we can't say that. So anyway, what minimum cost spanning tree is, this summation, the cost of the spanning tree, summation of cost should be minimized. So if the cost of the spanning tree is minimum, then we say it's a minimum cost spanning tree. So here the problem is minimization problem. The earlier problems of the greedy method, that is job sequencing with deadlines and and the knapsack problem, what we have seen was the maximization problems, where we were talking about how to maximize the profit earned. But here in this case, it is a minimization problem. That is, we have to find the minimum cost of the spanning tree. Now let us move further. So what will be the greedy approach? The greedy approach of building a spanning tree, which will be a minimum cost spanning tree, or constructing a minimum cost spanning tree, is to construct the tree edge by edge, taking one edge at a time. And the next edge which we try to choose should minimize the sum, should minimize the increase in the sum of the cost. So this is the greedy approach. Now there are two approaches here which we can use. One algorithm is known as Prim's algorithm, and the other algorithm is known as Kruskal's algorithm. So to find a minimum cost spanning tree, we can use either Prim's algorithm or Kruskal's algorithm. Both uses greedy approach or greedy method, greedy strategy, but there is a difference in both the approaches.